Hello and welcome to JD's Network Training. In this session, we're looking at LSAs 1 through 3 and the different areas of OSPF, not to be associated with stub areas, but having multiple areas in OSPF. So here's our OSPF topology. Everything through here is in area 0. Router 3s are area border router. Connects to area 1, area 2, area 3, area 5, back down to area 0, and over here is area 4. And I just did this to see if I could do it, and what happened was I created a virtual link between router 3 and router 4 because a router cannot be an area border router unless it has a segment directly in area 0. And it doesn't, so once you create a virtual link, it then become an area border router, but that begs the question, if this has a virtual link and is virtually in area 0, can you do that again? And the answer is yes. Router 6 and router 4 then have a virtual link, and it just keeps chain linking on to router 10, router 11, then I decided I'd put in area 0, and it's actually perfect right in the center here to get to router 1, so then we'll have equal cost multipath routing seen in router 11. And to get to 192.168.1, area 0 here, it costs the same. And it should be the same with 9, yeah, exactly right here. Network 9, equal cost. So first up, let's look at the LSA router type, which is type 1. So router 5 is in area 0. And the first thing we see coming up is a virtual link from router 3333. And the link state ID and the advertising router is both going to be the router ID for router 3. And it has a virtual link named router 888.4, which is right here. And its address 888.1 is right here. That's the virtual link connecting it. That is also advertised with a type 1. The stub network is the loopback. Loopbacks are always a stub. Even if you change the type to point-to-point, it'll still be a stub. The only thing you'll see is a longer mask. And we could check that out right now if we look at router 1. So it's got two loopbacks, 10.1.2 and 10.1.1. One was the default, where it advertises it as a 32 mask. And we changed 10.1.2 to 1 to point-to-point, so it actually advertises its actual mask, but they are both considered stub networks. Also, if you look at router 12, it's got a serial connection, and although it's a 24, it's also going to be considered a stub network. And while we're on the topic of LSA type 1 stubs, let's also look at so it currently says that this segment here is a transit network, but change that up, it's gig. Let's grab part of this. And the full adjacency shouldn't take too long. Once it's there, we should see all the LSAs. Oh, it's already there. So as you can see, all I did was change the mask, and now the segment is seen as a stub network because it's -30. And we could have networks behind it, but it's still going to be considered a stub. Same with the serial here, we can have networks behind this router, and this segment's going to be seen as a stub. And it's something you just have to understand with OSPF. So let's get back down to our LSAs now that we've covered all the weird stub issues. So we're again looking at router 3. We see its virtual link going to router 4. Stub is this loopback. And the transit network is area 0 here. Now we're at 66610. So try to keep this in the screen. Get it up. It's got a virtual link. Here's 6610. Its virtual link goes to router 6, which is 7776 right here is the router ID. And now we're looking at router 7776, which is router 6. And we're seeing all these LSA type 1s in area 0 because technically these virtual links are in area 0, and that's the only reason we're seeing them. If they were in their areas but they didn't have virtual links, you wouldn't actually be seeing that. There's this virtual link. And we're looking at 8.8.8.4, which is right here. And the virtual links. A lot of virtual links. And then 99991 right here, also in area 0. And it's showing as a transit network, although it should be a stub. Maybe just an update quick enough. That's fine. We know what it is. Now we're looking at 10.1.1, which is right here. Although not to be confused, and I did this kind of on purpose, with 10.1.1.1 loopback, I created overlapping addresses just to remind myself when I'm looking at routing communication that it goes by best route. So this loopback kind of looks like it's on this segment because it is a class C mask, but this address here is 10.1.1.2 and this is 10.1.1.7, so if you do route traffic it will actually go to this address. We could check that out too. So we'll see connected 10.1.1 on this link here, fastest unit 20, but when we trace out to 10.1.1.1, and you'll see it right there, it's intra-area because it's being advertised as the loopback. Interesting. Goes directly to 192.168.1.1 right here. Router 7 should be going to the longest route in its routing table, and it should be communicating. But we do not like shoulds. He goes to 2.2.7, then he forwards it to 1.2, and then so it routes from both sides, but router 7 couldn't get to it. It's very interesting. It made it to 1.2, but it can't make it back. Well, I'll capture that later and get that all figured out. Let's get back to where we're at. Router 10.1.1. Oh, these are coming from router 1. So the stub networks, there it's loopback, it's transit network over here, and it's point-to-point over here serial, although it's a /24, and it's shown the stub, and it's area 0 main transit right here. .3.3.9 is going to be, where is that guy? Right below us. And it's got a virtual link right here because this is area 0. And its virtual link went this way, whereas this virtual link went around that way. As you can see, it's with 1.2, and 1.2 is router 2. It's got the transit network, which is area 0. So now we're looking at 5.5.11, which is over here, our area 5. And we're seeing its transit network, area 0, which is 449. And it also has a virtual link. Now we're looking at 172.6.1.1, which is router 12. Point to point, its neighbor's router ID is router 1, and its interface address right here. Actually, correction, that's the neighbor router ID, but its address is 1.2. The link data router interface address is actually the address of the originating router, which is router 12, I believe. 1.1. Oh, it is the neighbor's address. Neighbor router ID, and then that's to be associated with the neighbor's address. And it's also considered a stub network because it's serial. Here we have 1.2, which is us, router 1. Wait, I'm getting a little sleepy over here. 1.2 is router 2. And it's got a virtual link shooting back over here to router 9, which is 3.3.9. The stub network is its loopback, and the transit is area 0. Now let's look at network, but let's look at it from router 5's perspective, because it's pretty interesting from over here. Let's open this up a little bit. So what we're going to see is kind of 3 different segments here, because they're from each area border router, or correction, designated router. Sorry about that. So there's a designated router on this segment for area 0. There's a designated router on this segment here for area 0. And there's also a designated router on this segment right here for area 0. And that's why we're seeing 3 different routers advertising 3 different segments here. And that's what this is associated with. So 9.9.9.2 is the address of the designated router, and these are the attached routers in this segment. 10.4.4.9 is going to be this segment in area 0, and the attached routers are 3.3.9 and 5.5.11. As you can see, 5.5.11 is right here, and that's network 3, that's 3.3.9. And then the last segment here is our main transit area 0 right here. That is 10.1.1.1 router 1. We're going to have router 3, and we're going to have router 2. Next we'll be looking at the summary. And this is going to be interesting. I created a little challenge, and I hope I catch it. I've misconfigured something out in the network, and I'm hoping to catch it as we go through this. So our area border routers are going to be represented by these summary LSA type 3s, and we'll see the link state ID. Here's a summary network for 6.6.6. The advertising router is 6.10. 6.10 is right here, and it's advertising this segment right here. It's a Class C mask. And then the 666 we'll see advertising also by this router, 777.6, because it's also an area border router in area 3. So they're both going to be advertising this area's network. And when it came up first, I'm glad it did. So we're also going to see one more router advertising the subnet 666, and it's going to be 8.8.8.4. And this is a little interesting. So if we look at 8.8.4 is this router right here. It's not an area border router for area 3. But gig 4 on router 4 doesn't actually connect to anything. So since this router actually can get to these networks, and it believes it's got an interface in area 3, it's still going to advertise area 3. Kind of find that interesting. Sometimes you have to misconfig to learn about things a little deeper. Yeah, here we go. So yeah, that was interesting. 8.8.4 isn't actually in that segment, doesn't have no connection to 6.6.6, but being how it's in its routing table, and it believes it's got a interface communicating, although it doesn't. It's still going to advertise it. So everything else is going to be pretty basic here. 7.7.7 is going to be represented by these two routers. Oops. Router 4 and router 6. And that's router 4. And then here's router 6. So then 8.8.8 summary network is, let's find it, right over here, going to be advertised by both these two routers. Router 3, router 4. And this is where OSPF is a link state routing protocol, because if I know where all the link states are at. So anything in area 0 from router 2, I know exactly where they're connected to. Let's look at router 1s. So here's router 1s. I know all the links that are connected to router 1. I know where they're at in the network and that they're directly connected behind router 1. Whereas a distant vector network, it works more like an area border router, where if I had a bunch of routers in area 1 here and they went kind of deep, I wouldn't know where they're at. I would just know that those routes are behind the router. I think we'll see that from router 2. Let's look at router 3 and let's look at area 4. And we're not going to know how, like 3.3, we're not going to know that it's behind router 7. All we'll know from router 3's perspective is that we got to go to router 2 to get to it. So we're going to have to look for the summary that's coming from 192.168.1.2. So we know from, here's our router, that 10.1.1.0 is behind it, but we don't know how far it's behind it. And we'll see that when we look at 10.2 and 10.3. So 10.2.0 advertising routers, 10.3.3.9. Yeah, we can also get to it this way, and that's why we're seeing it. 3.3.9 is being advertised out this way. But it's also being advertised from 1.2, and we don't know that it's directly behind it or how far out where it's at. We lose the full clear perspective of the network behind area border routers, and that's kind of how EIGRP works in its domain. Is if there's routers behind it and all kinds of routes, I don't know how to get to all the routes that are behind a router. I just know the distance, which is the cumulative metric, and the direction. That's what distant vector is. Distance is the cost, and vector is the direction. So here's 1.2 again, router 2. I know that 10.3.3 is 0 is behind it, but I have no idea what that network looks like behind here. I can see it visually here, that's the only reason I know, but I just know these networks are behind the router. And that's the main difference with link state and distant vector. is that OSPF's links state in general, but at the area border routers, it acts more like distant vector. So I think that's it for this session. I hope you've enjoyed it, and I hope you've learned something. Thanks for joining me.